I'm also incredibly lucky to be in the field of astronomy at this present time. Within the past 10 years, we have seen a major revolution that has changed the face of astronomy. And it's incredibly exciting to be part of that. And it's that revolution, that new window on the universe that I want to tell you about tonight. But one thing links all of these parts of astronomy together, which is that they are all made using light. Right? In all these cases, we are seeing the universe. We're seeing distant galaxies or distant stars with our eyes. And this new era of astronomy I want to tell you about today is the first time we've found a different way to observe the universe. And this will be using something we call gravitational waves. Okay, and this new window on the universe opened on the 14th of September 2015. So really not that long ago. And this new way of sensing the universe, you can think of as being akin to hearing the universe. So having these different senses on the universe, seeing it and also hearing it, and in the course of today's talk, I'll explain why I refer to it as hearing the universe. Having those two senses open is enabling us to learn lots of new things in astronomy that we haven't been able to before. So what we'll do today is I'll tell you something about gravity itself. Then we'll talk about what these gravitational waves are. Then we'll understand why we can think of them as the sounds of space-time. And finally, I want to tell you about one very special event that shows the power of combining this sight and this sound together. Now, I had to put an extra slide in my talk last night because something happened yesterday, and this shows you what an exciting field this is to be working in. So just yesterday, just before 2 o'clock, we had an alert of a possible new detection of a new gravitational wave event. Now, I realize I haven't told you yet what gravitational waves are, and this image might not make sense right now. I hope it will make sense by the end of the talk. But this was so exciting, I couldn't resist just not telling you about it. It's still early days. I have to say the data, needs more checks, so it's not confirmed yet. But this is what's happening. We're detecting these new events, regularly. Okay, but let's get back to our story. And the story is going to start with Sir Isaac Newton. And Newton formulated the first law of gravity. Now, there are only 2 equations in this talk, and I thought I would start strong and get one of them out of the way straight away, because it's an equation that I think a lot of people might remember from school, or maybe some of people who are still studying might meet it. So this is Newton's law of gravity. And Newton says that the force between the apple and the earth is given by the mass of one object, so in this case the apple, times the mass of the earth, and divided by the square of the distance between their centers. And there's a number in there we call g, which just makes the units work out correctly. Okay, so Newton's given us a recipe for computing gravitational forces. But he hasn't really told us what gravity is. He's just given this force prescription. And what gravity really is, why there is a force of gravity, wouldn't really be touched upon for a few hundred years, until it was picked up by Albert Einstein, arguably one of the most famous physicists of all time. Now, Einstein was definitely a person to sit and think hard about long-established scientific concepts, because, of course, Newton's law was long established by then. He has lots of really great quotes about human curiosity. So if you're ever having a down day at school or at work, go look up Einstein quotes. So he said something like this, right? The important thing is not to stop questioning. Curiosity has its own reason for existing. He was a curious person. However, he did also say, a table, a chair, a bowl of fruit, and a violin. What else does a person need to be happy. So I think Einstein might have lived a slightly different lifestyle from most of us. Okay, nevertheless, what's Einstein's big revolutionary idea? So here is a picture of the deep space, a deep patch of the universe. Okay, so every spot of light in this image is not a star, but a galaxy, okay, a collection of millions of stars. Now, I should stress that Einstein didn't have access to this kind of image. They weren't around in his day, which makes his kind of realizations even more incredible. So when we look at this image, in between the galaxies, we have blackness, patches of empty space. And it's very tempting to think of that as just being nothingness, void. But what Einstein realized is that space itself, empty space, is not just a stage on which the rest of the universe happens. Space itself is part of the action. So space has dynamics. That means it can move, it can warp, and it can bend and stretch. And Einstein realized what causes space to bend is the presence of massive objects. So we have a little patch of space over here. Now, of course, we're moving through 3 dimensions of space. And actually, in Einstein's theory, the correct thing to talk about is not just 3 dimensions of space, but he also folds time into there as a kind of 4th dimension. So we often say this word space-time, which kind of means the combination of space and time. But I can't show you a patch of 4D space-time. It's a bit hard to visualize. So this is my 2-dimensional patch of space here. And what Einstein's theory tells us is that if we have massive objects sitting in space, they effectively cause dips, dents, or wells. They bend that space around them like a piece of fabric. Okay, and the distortion they cause is proportional to their mass. So this is something really heavy. It causes a really big dent in space-time or space. If we have something much lighter, this might be, a moon, if that's a star like the sun, just causes a much smaller dent in space-time. Okay. So that's Einstein's big revelation. As I say, this is just a 2D example. We do have a 3D example, which makes it a little bit better, because of course our universe is not just kind of full of sheets of fabric. So here's a little 3D graphic, which I think shows the situation a little bit more clearly. So we've got this orb, this white mass, and it's moving round on a circle. And around it, there's this sort of grid of blue cubes. Those are meant to be representing this kind of 3D fabric of space. And you can see what happens as the orb moves. The space around it kind of bends. It gets sucked inwards almost. Okay, that's just a slightly better representation of Einstein's bending of space and time. Okay, so Einstein formulated all of this mathematically. Now, don't panic. We're not going to go into the mathematics of his theory today. But we can look at some of its main equations in word form. And this is what he published as his general theory of relativity in 1915. So the central equations of Einstein's theory say the following. On the left-hand side, they've got a bunch of mathematical objects which tell you about this bending of space and time. And they equate that to a bunch of objects on the right-hand side that describe what space contains. Matter, or even light and energy, if they're concentrated enough, can bend space-time. And so now we have a picture of what gravity is. When we have a small body, like a satellite or the apple, it feels this tendency to move towards the larger body because it's experiencing that distortion in space or space and time. And it has a tendency to move towards the bottom of that well, that dent in space-time. And that's what we experience as the force of gravity. Okay, so this is Einstein's big revelation, and he doesn't have to wait too long for some experimental confirmation of it. So luckily, 4 years later, there's a solar eclipse due. So the moon is going to come along and temporarily block out the sun, as seen from certain locations on the Earth. And Einstein spots this opportunity, and he makes a prediction for a particular effect from his theory during that eclipse. And what he predicts is that the position of stars around the sun is going to wobble. So, of course, normally you can't see stars anywhere near the sun. It's far too bright, it just blocks them out. Okay, but during an eclipse, of course, the moon is in the way, it blocks out the sun, and now, particularly if you've got a good telescope, you can see stars around the edge of the sun for a few minutes. And what Einstein's theory says should happen is that the positions of those stars should appear to move. So the light is coming from that distant star, you can see the blue line there, but it's getting bent as it travels through this curved space-time well of the sun. We receive it here on Earth, but when we look at that light, our eyes just trace it back in a straight line. So we see the star as appearing where that white object is, where it says apparent position, and actually the star is following the blue ray in the actual position. And of course, once the sun has moved on, as it continues, orbiting through the sky, the effect goes away. Okay, so this wobble is just there for a few minutes during the eclipse. So Einstein predicts all of this using his theory, and it is confirmed. The results are a little bit dodgy. It doesn't all work perfectly, but enough for the newspapers to proclaim this a success for Einstein's theory. Einstein's theory triumph. The best bit. Stars not where they seemed or were calculated to be, but nobody need worry. And so the idea at the time was that Einstein's theory was so complicated that only a handful of people on Earth would understand it. Okay, today we teach Einstein's theory to physics undergraduates all around the world. Okay, so Einstein had his theory confirmed, or at least he'd had some evidence for it confirmed. However, there's still a secret hiding in Einstein's theory. And to talk about this secret, I need to introduce you to some objects I think of as the ghosts of stars. So, when stars die, that is, when they've finished burning all their fuel that keeps them alive, as like the sun shining, when they've finished burning all that fuel, they undergo a spectacular set of processes in which they throw off a lot of their outer layers, and they leave behind a very, very dense core. And there's a couple of forms those cores can take, but we'll be interested in two particular types today. One is black holes, and the other is called neutron stars. Now, probably people have some kind of notion of black holes maybe coming from popular science, from Interstellar or something like that. So you might know that they are these sinister, scary regions of space which don't let anything out. It's more or less true. So a black hole is an ultra collapsed region of space such that nothing can escape, not even light. And what's happening in this simulation here, and this is a simulation, not a real image, is that you're seeing some gas that's about to fall into the black hole, and it's very hot, and so it's emitting light. And that's why in this case you can sort of see the black hole silhouetted against the gas. But once that hot gas has fallen in, you wouldn't see any light. Black holes are really, really massive. They start at a few times, roughly 10 times the mass of our sun, and they go up to maybe 100 times the mass of our sun. Okay, so they're really, really big things.